Debris flows, they happen naturally in natural landscapes, even in forested ones. But as the climate is getting more severe, more of the area is being burnt. Wildfires are getting more extreme and more widespread. In a landscape that is moderately or severely burned, the tree cover is gone and the soil ground is exposed to the sky, and when there is rain, this land is not going to absorb the water. Even the slightest bit of rain can accumulate the soil materials that is readily exposed, and they can mobilize downhill to the bottom of the watersheds. As you see, the more of the area is exposed, more rain accumulates, and they collectively get bigger and faster as they move down the watersheds. And where they start getting catastrophic or devastatingly bulkier, carrying the sediments, the trees, and the muds and the rocks. And as you reach the valley bottoms, that's where most of the infrastructure or property lies. Post-wildfire debris flow can be exceedingly fast and devastating flows. My doctoral work can be best explained in 3 simple steps. First is, how do we properly estimate how fast and how big can these post-wildfire debris flows be in these kind of environments? Second is properly mapping this microtopography and using computer simulations to estimate where this flow can go, and using climate models to scale up these flows. And we do that by doing numerical flow simulations on computers. The third and the most important step is, how do we actually mitigate this problem on the downstream where people and infrastructure are placed, and that is done by designing these small scale terrain mitigations as simple as a ditch and a deflection berm. But where do we actually place them, and how big they should be and how thick they should be, determined by how fast and how big can the debris flows be. And I fit these pieces together to design these mitigations on the downstream end of the watersheds to protect people and infrastructure.
I mean, some of the places that we've studied, the events are occurring within months of a fire, within 1 year, within 2 years. And so the window of elevated hazard is at least a few years and could extend up towards a decade. And so it's not as if the problem goes away immediately. Mother Nature does her best to start to repair the watershed and the landscape, but there's elevated risk and hazards that could last for multiple years. The awareness of the domino effect of a forest fire and the hazards that can be created because of the forest fire is increasing every year. Our drive in today into this forest, there's big signs warning people about the rock falls, landslides, debris flows that can be triggered in a burnt environment. And so those type of signs probably wouldn't have occurred 10 years ago. So our provincial agencies, regional districts, our municipalities are now becoming aware of these hazards. They do very rapid post-wildfire assessments to try to identify properties at risk. And then what's taking too long, and this is where Kaushal's research is coming in, there's opportunities to do low-cost mitigation to protect people's homes without a whole lot of extra study using the tools and techniques that Kaushal's developing.
I always wanted to work on the mitigation side of these landslides and debris flows, and I was looking for a PhD. I had experience doing the hazard assessments part, but never had a way to solve it through an engineering lens. And UBC Okanagan is the best place where I could imagine only this work can be done. I met my supervisor. He is a world-renowned expert in designing these mitigation structures. We came up with the idea that if we could do something that is relevant to this area, and especially we see these debris flows impacting First Nations and rural communities, and we had a few fieldworks that really trickled our curiosity and also a lot of emotions attached with the people living downstream. We sort of focused more on the mitigation side of events that can have big impacts on people's lives.